So the reason we care a lot about all this stuff is really the driving force behind the Industrial Revolution. How do we get heat to do work? And the answer is by using a heat engine. We're not going to get into the nitty-gritty details of the various types like the internal combustion engine or the external combustion engine like a Stirling engine or various other types of things, the diesel engine. We're not going to go into those kinds of nitty-gritty details. We're going to focus on the overarching theory that applies to all of them in their own way. So these are all known as heat engines, and they're all things that what they do is they extract heat from some sort of what we call a hot reservoir that can be created from burning coal or nuclear reactions or whatever else. And then they use some of that heat to do work, and then they expel the rest of that heat into the environment as exhaust. That is the definition of a heat engine. So heat engines are a cyclical process. They always end up back where they started on a PV diagram. You're going to watch them go from point to point to point to point to whatever, back to the original point where it has the same state variables, the same pressure, volume, temperature, and internal energy as it started. The first part of the process is where it absorbs heat from the environment. It pulls it in from your coal or your nuclear plant or whatever else. At some point in the process, waste heat is exhausted. It's removed through a moving fluid, typically water, which is why power plants tend to be built, say, on rivers. You get a nice influx of water that you can then heat up to do work, and then you can exhaust it out into the environment. A gasoline engine uses the air, the environment, in order to exhaust heat out that way through your exhaust pipe. It also radiates a bunch off of the engine block and so forth. The work done by the engine is subject to conservation of energy. It's equal to the amount of heat absorbed minus the amount of heat that was exhausted. Whatever's left over is the stuff that was able to do work. Functionally, mathematically, you can find that work by taking the area inside the PV diagram. The efficiency of any heat engine is equal to the work it did divided by how much energy it took to do that work, the heat absorbed. So it's the net work. There's going to be positive work when it's compressed. There'll be negative work when it expands. The net work divided by that Q hot, the heat absorbed, is your efficiency. You could also call that the percent difference between the heat absorbed and the heat exhausted. Same equation. So a heat pump is a heat engine that works in reverse. An example is an air conditioner or a refrigerator. We do work to expand a gas forcibly that cools it down. But to do that, we have to produce some more heat in other places. You expand the gas, and then you can use that to cool the inside of your fridge or your freezer or your house. And then the gas gets recompressed, that heat gets exhausted elsewhere, we forcibly expand it to cool it again, and so forth. This is why the back of your fridge is hot. The inside of your fridge is cold, but the back of your fridge is hot. Air conditioners hang out of windows for a reason. The inside part gets colder, but the outside part gets even hotter. That's a heat pump. The most efficient engine in the world was designed by a French engineer named Carnot, and it is known as the Carno Engine. And the Carno Engine is perfect in that it is the highest efficiency engine possible. It's not 100%, that's impossible, but it is as high efficiency as you can possibly get. And the Carno Engine comes in a specific cycle of reversible processes. And reversible just means that you're doing things so slowly that any given thing you're doing, you could do the opposite and get it to come back. If you're compressing a gas, it would be like adding a speck of dust at a time to the cylinder to get it to compress. And then to get it to decompress, you'd remove a speck of dust at a time. This does mean that our perfect engine isn't so perfect when it comes to power. It takes an infinite amount of time to complete each process. The Carno engine would generate 0 power. But it is the highest efficiency possible, and it gives us something to strive for when we're designing engines to say, can we get this thing as powerful as we need it, but as close to the Carno efficiency as possible? So let's take a look at what that looks like. So the Carno engine starts with an isothermal expansion. We connect our piston to a heat reservoir, and we heat it up at a constant temperature until it expands to a certain point. At that point, we remove the heat reservoir and allow its momentum to continue to expand it in an adiabatic expansion. From there, we attach a cold reservoir, we let it compress back down, and then we let its momentum carry it back to its original position again in an adiabatic compression. So it's an isothermal expansion, then an adiabatic expansion, followed by an isothermal compression, then an adiabatic compression. That is the most efficient engine possible. And interestingly enough, how efficient is it? It is the percent difference between the highest temperature and the coldest temperature in Kelvin. It's just hot minus cold divided by hot times 100. That's the efficiency of a Carno engine. That is as efficient as any heat engine can possibly be. Now the why is difficult. Why is that the most efficient engine possible? It can be pretty hard to understand, and we're not going to go into great detail on it, but we're going to touch on it a little, and then I'm going to refer you to another set of videos which are very, very cool. So in our next video, we're going to tackle the second law of thermodynamics and a little bit of the implications of it, but not too much. You could teach an entire class just on that law and what it truly means. And I don't mean an entire 42-minute class. I mean like an entire college class on the second law of thermodynamics. We're going to skim over the top of it in one video. See you there.